All right, thank you so much. Welcome everybody. This is Daniel speaking. Welcome to this DNSSEC session. This is the second session we are doing with you. Great pleasure to be here. And this is the last theoretical session before the laboratories that we prepare for you for configuring the recursive resolvers. So welcome, Nicolas, for this session, and the floor is yours.
Hi, thanks, Daniel. Hi, everybody. Good morning. Today, as Daniel mentioned, we are going to be reviewing DNSSEC extensions to the DNSSEC, to the DNS protocol. Sorry, DNSSEC. First of all, before starting, as we mentioned the last presentation, the last meeting, feel free to turn on your cameras. Feel free to interrupt or just ask for the mic or post your questions or your comments in the chat at any time. Don't wait till the end of the. Do not wait until the end of the presentation. Let's do this more interesting and dynamic for everybody. So feel free to at any time ask any question or any comment you have. You may have questions about what we are talking about. You may have comments about your experience. Oh, I did this way, or I thought this was this way, and if you want to make some comments based on your experience, those are very welcome. So feel free to do it. Okay, so let's start. I'm going to share the screen. Daniel, is the screen okay? Are you seeing the presentation? Yes.
Yes, perfect.
Okay. So if you can monitor the chat and tell me if someone has any question at any time. Okay.
Sure.
All right, and of course, if you have any comment, Daniel, feel free to do it. Okay, so what's DNSSEC? Okay, we are going through this DNSSEC protocol, which is actually an extension, a security extension to the DNS, to the standard original DNS protocol. So let's go very fast through some DNS stuff, and also let's mention some interesting features about, or some interesting facts about DNS and DNSSEC. As for DNS, you know that we normally have one packet for a DNS query and one packet for a DNS response. We are talking about the dialogue between the resolver and the recursive server. If you remember from last time, DNS, basically we talk about two types of servers. When we talk about DNS, we talk about authoritative servers, which are the ones that hold the information, the authoritative information for every domain name. That information is stored in the authoritative servers. And then we have the recursive servers, which are the ones in charge of searching for a certain information requested by any client. And once they find the information by asking different authoritative servers, the resolver will forward that information to the client. Okay, so this DNSSEC protocol will take place between the dialogue among recursive servers and authoritative servers. This is not between the client and the recursive server. This is not between any other stage in the DNS ecosystem. This is only between recursive and authoritative servers. Okay, so as I was saying, normally we have one packet for DNS query sent from the recursive to the authoritative, and then one packet in response from the authoritative to the recursive server with the answer or the best referral to the answer. Okay, so this is trying to show that that dynamic. I mean, the client will send the query to the authoritative server, and the authoritative server will typically reply to the client with the information the client is looking at. So in this scenario, yeah, the client has to trust the source address of the server. So when the client is contacting the authoritative server, it will trust, it will assume that the one that is answering, it's actually the authoritative server, and it is not some other server that is, you know, responding in behalf of the real authoritative server. And if someone manages to spoof authoritative server IP and put let's say a rough server in place of the real authoritative server, the client, in this case the recursive server, which will get the answer, will have to trust the information that is coming from the authoritative server. At the same time, if a client, say a browser, for example, that it's trying to reach a web page and needs the address corresponding to the web server, will send a DNS query to an authoritative, to a recursive server, right? So that client, that device will trust that the answer, that the DNS answer it's getting from the recursive server, it's correct. Okay, that is in the original DNS protocol. So there's no any security measure in place before DNSSEC. There's no security measure in place that will guarantee the client or the authority or the recursive server that they are getting the correct answer. So if they get a wrong answer, they won't know. Okay. Source addresses, of course, can be spoofed. There are many types of attacks, of DNS attacks that try to spoof DNS IP addresses of DNS server, and there are other attacks that try to modify the answers. So the answer that the client gets is different from the actual answer that the DNS server is giving. So the client gets a wrong answer with a wrong IP address on purpose, right? So an attacker will put his IP address instead of the real one, so the client goes and ends up going to a web server that is not the real web server but a fake one. For what? For anything but good practices or good behavior. So maybe some attacker can set up a bank account, a web server that looks exactly as my bank account server, and I access this fake server that I think is the correct one. I think I'm gonna think I'm accessing my bank, and I'm gonna think I'm getting the correct web page and the correct information, and I will be actually giving all my my bank account credentials to an attacker. So that is one of the reasons that we will want DNSSEC to be deployed. Okay, so this is kind of what we were saying. We have the client here, we have the DNS server here. The client sends a query, and then an attacker sends an evil response to the client in behalf of the server. So the client gets this, the red one, the evil response, instead of this one, and the client will end up having wrong IP addresses and accessing wrong information, or accessing the attacker servers instead of the real one. Okay, so this is when DNSSEC comes in place, right? Comes into action. So what is going to do DNSSEC? Well, DNSSEC is going to provide us the DNS ecosystem. Particularly, DNSSEC is going to provide the recursive server with a means to be able to actually verify that the information it's getting, the information the recursive server it's getting from the authoritative server, it has not changed. So no one changed the information while it was sent, okay? And at the same time, it will provide a means for the recursive server to verify the identity of the authoritative server, okay? How this is gonna be made, how this is gonna happen? Well, what is going to happen is that the authoritative server, besides providing a response to the recursive server with the information the recursive server is looking for, it is also going to provide an electronic signature. It's actually the authoritative server is going to sign the data it sends to the recursive server. So the recursive server will get the data as in a DNS world without DNSSEC, and also will get a signature, a digital signature of the data. So the recursive server will be able to somehow validate that signature and say, okay, this information I'm getting from this server, it's not modified, so no one tampered with that information, and also I'm getting information from the correct server because I can verify the signature and the signature is okay. Okay, so let's see how that works, how DNSSEC works. Before going into the DNSSEC details, we are going to review a few things about cryptographic basics. Okay, cryptography basics. So DNSSEC uses this what is called asymmetric cryptography or asymmetric encryption, which basically it differs from symmetric encryption. Symmetric encryption is when you agree with the other side, with the one you want to exchange information with, we agree with the other on a password, on a secret key that you will need to encrypt the information, and you will need the same key to decrypt the information. So when you encrypt and decrypt information with using the same key, that is called symmetric encryption. In contrast with that, we have what we call asymmetric encryption. When we are talking about asymmetric encryption, the key we use to encrypt information is different from the key we use to decrypt the information. So there will be one key to encrypt and one different key to decrypt the information. It also has the property that you can encrypt with any of them, but you need the other one in order to decrypt. So if I encrypt, let's say I have the two keys, okay? If I encrypt the information with one of them, I will need the other one to decrypt. And the other way around, if I use the second one for encrypting, I will need the first one for decrypting. Normally, we talk about what we call public-private key algorithms, okay? So these are cryptographic algorithms that are based on this asymmetric behavior or asymmetric function that I was talking about. So in this public-private key, we have one key that we call private and one key that we call public. So stuff that we encrypt with the private key, it can only be decrypted if we have the public key, and the other way around. But we are going to use it that way. So someone is going to encrypt using the private key, and to decrypt, in order to be able to decrypt that information, you will need the public key. Okay. All right. So that's for asymmetric encryption and private public key exchange. So how does this cryptographic algorithm works in order of being able for the DNS servers to provide or to be DNSSEC enabled? All right. First of all, let's see what is something that we call hash function. What is a hash function? A hash function is a cryptographic algorithm that produces a fixed size output of any string. So if we have, say we have a text of 1, 2, 3, 100, 1 million text pages, okay? And we apply that mathematical algorithm, call it hash, to that text, and we end up with a fixed in length with a fixed output, with a fixed string in length as the output. The other property that hash function has is that output, it's kind of encrypted. It's a kind of signature of the text. So if let's say we have some pages and we apply a hash function and we end up with a hash output, which is a fixed string in length. Okay, that if we change any character in the original text, the output will change. So any character that is modified in the original text, if we apply the same hash function, it will end up being a different output. Okay, and the other property that has is that if you know the output, even if you have the output, even if you know the algorithm that was used to generate that hash, it is not reversible. So you cannot get the original text from the hash. If you have the hash, there's no way to get the original text. It's only one way. You need the original text and you need to know the hash function in order to get the hash output. Okay, but you cannot go the other way around. You cannot go from the hash output to the original text. So the output is unique. If you change something in your original text, the output will change. And once you have the output, even if you know the algorithm, you cannot get the original text again from the output. Okay, that is a hash function. So this is an example when we have a text here. We have then we will use you have our public key. We end up with an encrypted version of the text. Then we can use the private key in order to decrypt this and get again the original text. The same happens if we use the private and the public key the other way around. If we have the text and we encrypt the text with the private key, we get here is this original text encrypted. Then we will need the other key, the public one, to decrypt. Okay, this is an example in order to show how public and private encryption works. Stuff we encrypt with the public, we need the private to decrypt. Stuff that we encrypt with the private, we need the public to decrypt. Okay. Then we talked about the hash. So if we have the text and we apply the hash, we will end up with a unique string, and this string is also fixed in length. So no matter how big, how much text, original text we have, we will end up with the same length string at the end. The only thing is that this string will be different for each text. Okay, that is the hash function. Once we have the hash function, if we encrypt this hash with a private key, we will end up with what we call a digital signature. So what's a digital signature of any original text? Well, a digital signature then will be to, first of all, apply a hash function to the text in order to get a fixed string, a fixed in length string. And then we are going to encrypt using the private key this hash. Once we apply the private key to encrypt the hash, we will end up with an encrypted string, that represents the digital signature. This is the digital signature of the original text. Okay. Why this is a digital signature? Well, this is a digital signature if we can, having the signature, if we can verify the authenticity of the text, right? So, given that we have the signature, let's see how we can verify that this signature corresponds to this original text. We have the signature, okay? And we also have the original text, because digital signatures are not meant to hide the data. They are meant to verify the data. So digital signature and text, we have all that. We have the original text and then the signature. And we want to verify if this signature corresponds to this text, okay? We have the text. We know that if we apply the hash function, the same hash function that was originally applied to the text, we will end up with the hash. We will end up with the same hash as the original one, okay? So we have the text, we apply the hash, and we have the output, the hash output which corresponds to the text. We also have the signature. The signature was created using the private key. Remember that we encrypted the hash using the private key. So in order to decrypt the signature, we need the other key, the public one. So we have the signature, we apply the public key to the signature, and we get the hash, okay? Because the hash was encrypted using the private key, and now the signature was decrypted using the public key. So we get the hash. If we compare these two hashes, if we compare the hash we obtain from the text and the hash we obtain from decrypting the signature, if these two matches, then this signature corresponds to this text. Why? Because if anything in the text is modified, this hash will be different. And when we decrypt the signature using the public key, we will get a hash that is different from this one. So these two won't match if anything is modified in the text. Okay, so this way we have a means to verify that a signature, a digital signature, corresponds to a certain original text. Okay, what we need for this, we need the text, we need to know the hash algorithm that was used originally to generate the signature, and we need the public key. Why this cannot be tampered? Because we only know the public key, we don't know the private key. The only one that knows the private key is the owner of that key, and that key won't be revealed, won't be sent to anyone. It will be kept in secret by the owner of the key in order to be able to sign the text he or she produces. Okay, so as we only know the public key, we are not able to generate signatures. We are only able to verify signatures. On this way, when you get a text and a digital signature, you will be able to say, okay, if the signature verifies, that means that this text is the original one. No one tampered with the text. And also, you will know that the one that sends the text is the one that is meant to be the owner of the text, the one that wrote that text, and not someone that is, you know, acting in behalf of the real owner. Because if someone tries to send the text pretending to be a different person, as that attacker won't have the private key, it won't be able to generate the correct signature, right? So the trick here is, first of all, always keep the private key secret. So the private key will only be known by the owner of the information. And then there's another thing that we have to always bear in mind, that is, we have to be able to provide the public key in a secure way. Okay, so everyone should get the public key from the owner, the original owner of the information. Because if an attacker uses a different private key to sign the text and manages to send me his or her public key, I will have the public key that corresponds to that private key. So I will be able to decrypt and verify the signature, and I will think that this text was originally made, but someone that is not the one that is the owner of the information. Okay, so private key is going to be kept always secret, only known to the owner of the information, and the public key, we are gonna distribute the public key in a secure way, so everybody knows that the public key comes from the original owner of the data. Okay, this is how a digital signature works. We are going to see in a few minutes, we are going to see how this digital signature is applied to the DNS in order to be able to provide DNSSEC, okay? Before continuing with this, I'm going to ask you if you have any questions or any comments up to this point. Daniel, I don't know if there's any question or comment in the chat.
I think it's a good time to stop and see
Okay.
if somebody have any comment. I just would like to say that please don't worry with the complexities of this technology that Nico just explained. This is something that it's very nice to know how it works, and this is the reason why we are providing so much details. But in the day-to-day operations, this technology works for you. So the idea for this be using cryptographic keys, being complex, is just to make a robust technique for preventing some types of vulnerabilities or attacks to the DNS. But this is all the work of the machines, okay?
Yeah, I mean, yeah, as I mentioned, you don't have to know everything about this, and you won't need to remember all of this in order to operate a DNS server with DNSSEC deployed in a daily basis. It's just something that you need to know once if you want to go deeper into this, or if you want to know more about this, how this mechanism works. You can go, of course, you can go to the DNSSEC standard specification. You can go to the RFC and get all the details about how this works. And of course, this has a lot of mathematics and cryptographic theory behind. But again, as Daniel mentioned, this is not necessary in order to operate a DNSSEC enabled DNS server. Mm-hmm. It's just something that we present to you in order for you to know what's happening behind this protocol. Okay, what the machines are doing, but it's not something that it's necessary for you to remember in order to operate a DNSSEC server. Okay. Once again, if you have any questions or you think I'm going too fast, just tell me, okay? There's a question here, right?
Nicholson, yes.
Yes. Please
so
read
what is the difference between NSEC 3 and the DNSSEC?
Excellent question, Nicholson. We are going to go through that in some minutes. First, we are going to explain how this digital signature applies to the DNSSEC, and then we are going to see what's NSEC 3. We're going to mention what's NSEC 3 and what is the relation between, or the difference between. Actually, it's not a difference; it's a relation that is between NSEC 3 and DNSSEC. Okay, and yes, it's true what you're saying. Both use hashing mechanisms and signing. And yes, actually NSEC 3 is part of DNSSEC protocols. Okay, DNSSEC it's a security extension that actually make use of different protocols. For example, some of them are these hashing mechanism, private and public key exchange mechanisms, and other protocols that are used by DNSSEC in order to provide the security we mentioned. NSEC 3 is one of those protocols, and we are going to mention what is and how and what's the purpose of NSEC 3. Okay, we are going to go through that. And Daniel, if I skip that, just remind me that I have to talk a little bit about NSEC 3. Okay.
Sure.
All right. So we have this digitally signing mechanisms we explained it. We basically, again, to recap, we have a data, a text, we want to sign, we make the hash of that, we get a fixed string in length, then we apply the private key to that string, and we have this digital signature. In order to verify the digital signature, we need at least 3 things. We need the original text, we need the hash algorithm that was used, and we need the public key. With the original text and the hash, we do the same. We apply the hash to the original text, and we save that. Then we have the signature and the public key. We apply the public key in order to decrypt the signature and obtain the hash. and then we compare the two hashes. If the two hashes matches, signature is verified. If the two hashes does not match, then something is wrong, something has changed in the text, so that signature, it is not corresponding to the text, so something may have happened. Okay, either someone tampered the text, either someone is tampered with the signature, so the signature is false, or either someone sent me the wrong public key or whatever, but in any case, that's not the signature corresponding to the text, so you have to open your eyes, okay? Okay. So Rohan is asking to clarify what I mean by saying DNSSEC is not meant to hide the data. Okay. DNSSEC, as we mentioned, it's a protocol that it's, as I said, it's a protocol that it applies between or acts between the recursive server and the authoritative server. So when the authoritative server sends answers to the recursive server, it will sign those answers, but it won't encrypt the data. So the data is still sent in clear text. Anyone in the middle can see what the authoritative server is sending to the client. So data is not encrypted. So it's not providing privacy. You know, when we talk about hiding data, we are talking about privacy. So it's not an encrypted channel between authoritative and recursive. It's just the authoritative signing the data it sends to the recursive. Okay, but again, the information is not encrypted, so it's not hiding data. It's only providing a means to verify a signature. Okay. Okay, perfect. So I hope that answers that, or at least clarifies a little more your question, Rohan. And thanks for the question, because that is one of the main or the most important things we have to remember about DNSSEC. DNSSEC is not providing privacy; it's only providing security in order to be able to verify a signature. Why we want to verify the signature? Because we want to make sure that the one that is sending the data is the owner of that data, the real owner of the data, and we also want to verify that no one tampered with that data while it was sent. Okay. Okay. So here in this slide, it's exactly what we're talking about. What DNSSEC does, or what DNSSEC provides. DNSSEC uses public key cryptography and digital signatures to provide two things: what we call data origin authentication. So this means that does this response really come from example.com, Zone Authority, or it is coming from another place that is not the original one? So it's been sent by an attacker or another server. So that is origin authentication, to be able that the origin of the data is the real one and not a fake one. Okay. And then it also provides data integrity. That is, the data wasn't changed, it's not tampered when it was sent or while it was in transit from the authoritative to the recursive. Okay. So if an attacker, what is normally called a man in the middle, modifies, or a person in the middle, modifies the data in this response, since the data was originally signed, the recursive server will have a means to say, hey, this signature does not verify, so someone has changed it or someone has tampered with the information. Okay, or the information comes from a fake server. So DNSSEC offers protection against spoofing of DNS data, and so for attacks like cache poison and other kinds of attack. In a later presentation, we are going to go through some of the main or some of the most known and important types of DNS attacks. this attack called cache poisoning is one of the most known and most problematics in the past. And this is this kind of attack called cache poisoning is the reason that people from IETF developed DNSSEC. DNSSEC was originally developed in order to prevent cache poisoning attack, and also also to provide this data origin authentication and data integrity we are talking about. Okay, so DNSSEC provides security by verifying a signature. It does not provide confidentiality of DNS data, so there's no encryption of the data. Okay, and transfer data will be readable by a person in the middle. Okay, and of course it does not address attacks against DNS software like distributed denial of service, packets of death, and other attacks. DNSSEC won't prevent that attack, so DNSSEC is not the solution to every attack or to every problem, but a very robust and reliable solution for these two things, again, that are the most important: data origin authentication and data integrity. Okay, so how DNSSEC works. Okay, in our last presentation about reviewing or recalling DNS and how DNS works, we talked we mentioned that, or we remember that we mentioned that each DNS server, each authoritative server, has a file where it will store all the information for that zone. Okay, that is called the zone file, and the zone file basically will have all the information of all the domain names within that zone file, right? DNSSEC, it's some on the authoritative server side, it's something that we will have to do, or we'll have to store more information in the zone file. What other information is going to be stored in the zone file? Well, we are going to take every single piece of information that is in the zone file, and we are going to sign all those. So we are going to sign every domain name information that is in the zone file, and we are going to store that signature in the same zone file. Okay, all right. Again, important, in DNSSEC, DNS data is signed, not the messages. Okay, so we have a lot of information in our zone file in the authoritative servers. We sign each and every entry we have in the zone file, and we store in the same zone file those signatures. So we will have now the information for a certain domain in the zone file and the signature for that information, another information and the signature for that information, another information and the signature for that information. So all information will have its own signature. Okay, again, how we perform that signature? Well, ideally we will perform that signature not in the same server, in a different one. Okay, using our private key. We will take the information, we will apply the hash to the information, and then we will encrypt that hash using the private key, and then we produce the signature for that information, and then we store in the zone file that we have the information, and now we store the signature for that information, and we do that for every single entry we have in the zone file. Okay, so we end up with a lot of information that we already have and the signature for each of them. Okay, can we do the signing in the same server? Let's say the information changes a lot because we operate a CCTLD, for example, a country code TLD, and we have a lot of entries in the DNS that we are always adding, deleting, or changing entries in our DNS. So if we do that in a different server and then we copy the information, the signatures to the server, that will take a lot of time. Yes, we can do the signing in the same server. There are sometimes there are some good practices and recommendations. If you do that you have to take into consideration, we will go through them at the end of the presentation. Okay, but yes, of course, you can do the signing in the same server when you work in the same authoritative server, and that is normally what you do when you have a lot of entries that changes in a daily basis. For example, when you operate a TLD or a CCTLD or a domain that it's always, you know, adding new entries or changing stuff. Okay. So let's go to this information that we have to store, this new information, these digital signatures and new information we have to store in the SOM file. Okay. Recalling what a resource record is. When we talked about DNS in our last presentation, basic stuff, basic concepts of DNS. In the SOM file, there are these resource records that are the containers of information, of the information we store in the SOM file. For example, there's a resource record for each type of information. Remember that, for example, to store a SOM file, to store the IPv4 address corresponding to a certain domain name, we have this resource record called A record. So A type record stores the IPv4 address for a certain domain. Then we have the quad A record. The quad A record stores the IPv6 address for a certain domain. Then we have the MX record that stores the email server name for a certain domain name, and so on. Okay, so we have many resource records in our SOM file, and now we are going to sign each of those resource records. We are going to generate a digital signature for each entry and store that in the SOM file. In order to do that, DNSSEC creates new resource records. So other from this resource record we talked about last presentation, A record, quad A record, NS, SOA, CNAME, MX, PTR, and all the others, there are new resource records created by the DNSSEC protocol. And those new resource records are mainly three records. One is the record that is called RRSIG, RRSIG. The resource record called DNS key, and the resource record called DS. The resource record called RRSIG is the resource record we are going to use to store the digital signature. So once we sign our entry, for example, we have these domain names correspond to this IPv4 address. Okay, we have that we already have that in our SOM file. We take that, we generate a digital signature for that using the process we already explained it, and we store that digital signature in the same SOM file in a corresponding RRSIG record. So we are creating an RRSIG record that corresponds to that IP domain name record, that is an A record, to store the digital signature. We also mentioned that in order for a client, in order for the resolver, for the recursive server to be able to verify the signature, we need the signature. Okay, we already have the signature in the RRSIG record. We need the hash algorithm, and we need the public key. Okay, the public key, it's going to be stored it's also going to be stored in the SOM file in a new record that is called DNS key. So the DNS key is a record that holds the public key. Okay, and then we have this DS record that is called delegation signer record, that is meant for something called chain of trust, that we are going to go through that in a few minutes. So up to this point, remember that digital signature is going to be stored in a new record called RRSIG, and public key is going to be stored in a new record called DNS key. Okay, good. Let's see if there's any question. Okay, so Gordon was making a comment on about his resolver. It's not validating DNSSEC. One of the scopes of this capacity building series or presentation series is that next presentation is going to be, as Daniel mentioned, is going to be a hands-on lab in which you are going to be able to configure from scratch. You are going to configure from scratch a resolver. You are going to install a resolver. You are going to configure a DNS resolver, and you are going to enable DNSSEC validation in that resolver, and you're going to test that resolver. And it's not going to be a simulation. It's not going to be a test resolver. It's going to be a real resolver in the real internet, and it's going to be working, and you're going to be able to use that resolver you install and you configure to do DNS queries and get the answers from authoritative servers that has DNSSEC enabled. So you're going to be able to do that in the lab, and then the idea is that you will have the knowledge to go and deploy DNSSEC or enable DNSSEC validation in your resolver if you happen to operate a real resolver, a real DNS server. Okay. So let's talk a little more. We are going to go quite faster at this point. We are going to review how these new resource records are used, and we are going to review the process we already mentioned and the relation to these records in order to know how DNSSEC works specifically with these new records. Okay, so we will have the original resource records that we have before enable DNSSEC in our authoritative server. We have this A record. We have this quad A record that has either IPv4 address corresponding to a domain, or IPv6 address corresponding to a domain, or mail server name corresponding to a domain, etc. We have all these resource records. We want to sign them. Okay, so this here represents those resource records we want to sign. This is something that DNSSEC calls RR sets. RR sets are groups of same type resource records. So all resource records of the same type, let's say all quad A resource records are an RR set, and all A records corresponding to the same domain name are a different RR set, etc. So we have these resource records we want to sign. What is the first thing that authoritative is going to do in order to produce that digital signature? It's going to apply the hash function to these records we want to sign. Once it has the hash, it will apply this orange means the private key. It will apply the private key to encrypt that hash. So resource records are hashed, and then hash is encrypted using the private key. That string we obtain from encrypting the hash of the resource records is the digital signature. And authoritative server is going to store that digital signature in the RR site record. Okay. In order to do that, there's a key pair, a private and public key that is called ZS key pair. Okay, so this is what in the DNSSEC language it's called the zone signing key pair. So we generate a public and private key. We keep our private key secret. We use it to generate the signatures and store the signatures in the RR site record in our zone file. Okay. Then we mentioned that there is this new record called DNS key that will store the public key. So the owner of the authoritative server then takes its public key and store that key into the DNSSEC, into the DNS key record. Okay, so we have up to this point we have two new records: the RRC, which is the digital signature of the resources, and the DNS key that holds the public key. Okay. How a resolver can verify the signature? Okay, when a resolver asks something to an authoritative server that has DNSSEC enabled, the authoritative server will send the answer. It will send, okay, this is the IPv4 address corresponding to this domain name. This is what you're looking for. But also, it's going to send these new 2 records. It's going to send the answer that it's looking for. It's going to send the RR side record corresponding to that answer. So this is the digital signature of the answer, okay? And it's going to send the DNS key. Remember that we produced these 2 stuff, these 2 new records. We produced it in the past and we stored it in the zone file. So now authoritative servers with DNSSEC enabled are sending not only one piece of information, the response that the resolver is seeking for, but it's also sending the RR side and the DNS key. It's also sending the signature of the information and the public key. The public key is in the DNS key, okay? Then the resolver, what is gonna do? What operation is the resolver going to perform? Okay, the resolver is going to take the digital signature of the information, the RR side. It's going to use the public key, the DNS key record that holds the public key. It's going to combine RR sign, which is the signature, with DNS key, that is the public key, to obtain what? The hash. Because public key will be able to decrypt the signature, obtaining the hash. But then the resolver also has the information. So it will save this hash obtained by decrypting the digital signature, and it will take the information and it will apply the hash. What hash? Because the resolver also will know the algorithm that is being used by the authoritative. So it's okay, it's going to take the information, apply the hash to this information, and then it will compare that hash obtained by hashing the information and the hash obtained by decrypting the digital signature. We'll compare those two, and if those two match, then it's verified. There's no tampering of the information, and the sender is the original sender. It's the owner of the information and not someone in behalf of it. If those 2 hashes does not match, then information is not verified and there's something wrong with the information. Either someone tampered with information, either I have a false signature, okay? That is how, basically, how the DNSSEC process takes place between the authoritative and the recursive. Then there are a few things that we need to know in order to be able to make sure that we have the correct information from the authoritative server. Because up to this point, someone may ask, hey, this is great. I understand how it works, but what about this? What about the public key you send in the DNS key? What if someone changes this key and sends me a fake public key that corresponds to a fake private key? I will have the wrong public key, and I will be able to verify it because someone tampered the information and signed it with a fake public key. So the process of distributing this public key must be secure. Okay. In order to do that, there are other stuff that takes place. That there's another key pair that it's called the key signing key, which is a combination of public and again, it's a different public and private key that it's used to sign this new record. So these new records, this new record that DNSSEC creates are also signed with a different key. And there's a process to verify that key. We are going to skip that, and we are going to go straight to this DS record we mentioned. Remember that we said that DNSSEC introduces these 3 new records: RRC, the one that is used for storing the digital signature; DNS key, the one that is used to store the public key; and this DS, delegation signing. What is this record? Okay. If suppose that you are the resolver, you get from the authoritative server the information, you get the public key, and you get the the digital signature, and you are able to verify all that using the process we already mentioned. Okay, fantastic. How we can make sure that basically the public key we get from the recursive, it's not tampered, hasn't changed it. It's the original public key and not someone that was in the middle of that and changed that in order to make me have a different public key in order to be able to falsificate the signature. Okay. This is when a process called chain of trust comes into action. What is chain of trust? Remember that the DNS, it's an inverted tree, right? When we have the root at the top of the tree, and then we have the logs and the nodes of this tree are the different domain names. Okay, so we have a tree that represents the DNS database infrastructure, and we have domain names that are nodes into that tree. Okay, so each domain name, each zone operator, each domain name operator, a domain name will have a father. Okay, and then that will also have a father, and that way up to the root. So the only node that does not have a father or mother is the root. Okay, each other node has a father. Okay, so the one that is going to certify that you are getting the correct public key is the father of that node. How is that achieved? Okay, we mentioned that we have an entry in our zone file. We will create a digital signature, and we will store that signature in the RSI renew record. We are going to store the public key in the DNS key record, and we're going to create this DS record. What is the DS record? Well, the DS record is our public key. We will apply in the authoritative server. We will take that public key that is stored in this DNS key record, and we will apply the hash to that record. So we will apply a hash to the public key, and we will send offline the owner of the zone administrator of the authoritative server will send offline that hash to the operator of the father domain. Okay, that operator of the father domain will sign that information with its key, and will store that information in a new record called DS record. So this DS record, it's really not in the same zone file as the recursive server, but in the father zone file. Okay, each authoritative server operator will do the same with its public key. Remember that you will have one public key and one private key for your whole zone. You will use that key to generate the different signatures for each entry in your zone file. So you will have one public key and one private key. You will keep your private key secret, and you will take your public key, apply the hash, and send it to your father. Your father will sign it and store it in a DS record. Your father will also take his public key, will apply a hash, and send it to its father. And that father is going to also store that into a DS record, sign it, and store that into a DS record. And that is going to be repeated up to the root. Okay. So when a recursive server is in the process of verifying a signature, the recursive server will be able to ask to get the DS record from the father and verify that DS record. Then we will get the DS record from the father of that father and verify that DS record. And then it will go up to the root until he gets the DS record from the root and verifies that. Okay, and up to this point, someone may ask, hey, but the root server, the root operator, the root has no father. So who will verify that you are getting the correct key from the root? And at this point is when a process called root signing protocol or root signing process take place. What is the root signing process? Well, the root signing process, it's a standard procedure that it was created also by the IETF in order to generate, distribute, and protect the signature for the root zone. So the root zone will also have a private key and a public key. The public key of the root zone will be published, will be made public, and the private key of the root zone will be kept secret and secure in a facility. We can talk about that in future presentations, how root signing process is made and how this protection or this security of the root zone signing key it's done. But basically this is done by a process that involves the internet community and involves people that are called crypto officers that hold credentials to be able to go to a secure facility that holds the private key, and in order to generate the signature for the root zone. Luckily, the root zone does not change very often, so this signing of the root zone process does not need to take place very frequently. It actually take place every time a new top-level domain is created or a top-level domain changes in order to sign it again. And yeah.
We have one question from Rohan.
Okay.
About, does configuring DNSSEC on a zone for the first time always include a manual interaction with the parent to share the hash value for the DS?
Yes, the short answer is yes. You are completely right, Rohan. Every time you generate for the first time your private and public key pair, you will have to hash your public key and send it to your father in order for him to store it in the DS record. And that has to be done manually each time you recreate or regenerate or rotate your public and private key pair. If when you are for the first time enable DNSSEC in your authoritative server, you're right, you have to generate your public key and you have to send it to your father in order to generate that DS record. And every time you change your public and private key, you'll have to do the same. And that is done manually and offline. There are some methods, some good practices in order to do that. But basically, it's a relationship between you and your father domain and how you want to exchange that information. Of course, probably you are not going to, jump on a plane with a USB drive with a public key and go to give it in hand to your father domain administrator, but you are going, for example, to agree on a secure channel. You are going to set up an encrypted channel between some server you administer and some server your father domain administer, and you're going to send this through that secure channel. And of course, you will need a means to set up that secure channel, but that's up to you. Basically, there are many ways of achieving that. But yes, it is kind of rather manual process, but luckily you will have to do it once, the first time you are setting up your zone, and each time you change basically each time you change your KS key. Okay, each time you change your key pairs, you will have to do that again in order for create a new DS record for the new keys you have. Okay, You may ask, hey, okay, and how often it is good to rotate the keys? How often should I have a new key pair and discard the old one? Okay, that depends on how sure or how you think about your security. But if we go through statistically, if we go through the real domain names that already have DNSSEC deployed, and the periods or how often they rotate their keys, they are rotating their keys sometime between 6 months and 10 years. So there are those that rotate the key every 10 years. There are those that rotate the key every 6 months. Normally CCTLDs are rotating the keys more frequently. They have a process to rotate keys to generate new key pairs and delete the old ones each 6 months, and some others would do it, yearly basis, and some others may do it each 10 years. For example, the root key, the key for the root zone, since DNSSEC protocol exists, that was in 2010, it was only rotated once. So actually the key for the root zone, it's being rotated every 10 years, more or less. So it was rotated once since its inception in 2010, 2012. Okay. That is, it was originally planned to be more frequent, but this then the operations of that have demonstrated that it's not necessary to rotate the key for the root zone that often. One may think that 10 years is a lot of time, but again, the key for the root zone is not used very, very often, and it's kept. There's a very tough and high protection mechanism and protocol to make sure that that key won't be disclosed. So the security of that key it's very, very high, given the actual standards for securing keys. So it does not represent a major security breach to rotate it every 10 years. If we are talking about a top-level domain or a CCTLD, that's a top-level domain for a country code key. In that case, I mentioned that you may want to do the signing in the same server you have the information, because information is changing a lot. So it's not very practical to take the information out, sign it, and put it back in the server. So normally you are doing the signing in the same server. So that will expose, that will have more security risks, of course. Things that are practical normally comes with less security. So there's a trade, between security and practical. So that's why they normally rotate the key more often, like 6 months or in a yearly basis, because those keys are more exposed that the key for the root zone, for example. Okay, but that's the real story. I mean, the root zone has been only, the root zone key has been only rotated once. And if you operate a top-level domain or a CCTLD or any other domain that you do the signing in the same server, you will probably want to do the key rotation more often, like 6 months, 1 year, 2 years, but not 10 years. Okay,
Nico.
Yeah.
One more question: what keys can be automatically rolled without the manual interaction with the parent?
Well, okay, we mentioned that we have two keys. We have the ZS key and the KS key, right? So here it says changing CS key is easier than changing KS key. That also allows for having smaller ZS key compared to the bigger KS key and reducing the amount of data you're changing. So the key that you use to generate the DS record and all the stuff and to put it in place will be the KS key. So the one that you can change is the CS key. You can change the ZS key without mainly without the need for changing the KS key. Okay, that is why we use two different keys to perform the operations. But when we are talking about rotating the keys, we are talking about rotating both of them. Mainly, we are talking about rotating this KS key. Okay, so you have to interact with your file. Okay, you can, for example, say, okay, I'm going to rotate the KS key every 2 years, and I'm going to rotate the ZS key every 6 months. Okay, and that is maybe a good trade between security and practicality between, you know, all the things you have to do when you change the KS key. But or I can change the KS key yearly and the CS key every 3 months. I don't know. You have to find out the most suitable method or process according to how secure or how exposed your keys are. Mainly, you have to see if you are doing the signing in the same server or you're doing the signing offline. If you are doing all the signing offline and you keep your private keys out of any internet connected server, then you don't have to rotate the keys that often. But that is not normally the case for domains that have more frequent changes to their zone files. Okay, if your zone file is changing a lot, you will do the signing in the same server because that's the easy way, and you will have to rotate your keys more often. But yeah, you can rotate your ZS key every 6 months and your KS key every 1 or 2 years. That's okay. 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 Some resolver considerations. Up to here, we already gone through how DNSSEC works, what it is, and now we're going to mention some considerations if we are talking about resolvers. Okay. Of course, we mentioned that we have authoritative servers and we have resolvers. Authoritative servers is where most of the work has to be done regarding DNSSEC, because authoritative servers are the one that will hold all these records, that will hold all the digital signatures. Authoritative server is where you have to sign stuff, when you have to keep a private key and a public key, and you have to do all the stuff. Recursive servers or resolvers only gets the information from the authoritative servers and verifies the signature. So both of them have to need to have DNSSEC enabled. If one of them has DNSSEC but the other does not, then DNSSEC won't work. Okay, you have to have DNSSEC in the authoritative server, and you have to you will need a resolver that is DNSSEC enabled. So how about the resolver? Okay, some considerations are, remember that the job of validation resolver is to look for additional information that can be used to computationally verify a set of responses, that is to verify digital signatures. What about CPU of resolvers? So if I enable DNSSEC, will my resolver CPU blow up? No. Why? Well, validation, of course, it's basically performing cryptographic operations, cryptographic functions. So the resolver will have more stuff to do. So it will, for sure, it will have more CPU usage, okay? But that doesn't mean that your CPU is going to go to the clouds and you're going to end up losing your resolver because you enable DNSSEC. No, that is not going to happen. That is very, very, very unlikely to happen. Why? Well, because basically up to today, there's no it's not that all the domains have DNSSEC enabled. Actually, if we take, for example, .com TLD and all the .com domains that exist today, so all the .com childs that are signed with DNSSEC, only between 3 and 4% of all the .com subdomains are signed with DNSSEC. So that's, and .com is the one that holds the most domains in among all the DNS top level domains. So if .com has only 3 to 4% signed childs, you can make sure that if you enable DNSSEC in your resolver, there's going to be a small amount of DNSSEC validations, because there are not much authoritative servers with DNSSEC enabled yet. So you will have time to monitor your server and see how the CPU and how the resources of your resolver evolves. So you will be able to grow and to scalate your resolver as needed. It is not something that is going to happen to your resolver, that your memory or your network is going to blow up just because you enable DNSSEC. So it's very, you will see that it's very easy to enable DNSSEC. It's very, very easy to enable DNSSEC in a resolver. Of course, you have to monitor your servers. Of course, you have to monitor your memory. You have to monitor your network traffic. You have to monitor, because you have to monitor your CPU. But if you operate a resolver, you probably already do that. If you are not doing that already, you are already not performing some essential tasks. So you'll probably already have monitoring in place. DNSSEC basically will not add additional or many additional monitoring stuff to your server. It's the same stuff you've been monitoring all these years, that you will have to keep an eye on and say, okay, yeah, we will enable DNSSEC. Okay, we enable DNSSEC and we monitor. We have a look at that for the first 1 or 2 months in order to see how this evolves. If we need to if we need to add memory, or if we are getting a lot of more traffic because of DNSSEC. That's not likely to happen again, but of course you have to monitor your servers. Okay. System memory, again, DNSSEC, it won't make your memory grow a lot. Actually, the resource that consumes most of the memory at resolver level is the cache, and DNSSEC won't add much more memory to what you are already using. Of course, now you have the information, and now you have additional resources. You have, for each information, you now have a key to verify the information, and you have the public key, and you have the signature for that information, and you want to store that in memory in order to be able to verify it. But again, that is not it shouldn't be a problem, and it's not representative if you compare it to all the memory that a resolver consumes where caching. So again, memory shouldn't increase significantly when you enable DNSSEC. Network interfaces, network traffic, okay, there's more information to be sent because you are sending the data plus the signature plus the public key plus DS records and all the stuff. But again, that won't mean that your network is going to need upgrade, or you're going to increase bandwidth or to your server or whatever. Normally, network traffic to DNS server, it's not an issue, given that today every server interface is practically, the minimum is kind of gigabit of bandwidth. So that won't be a problem, right? Again, you're probably already monitoring your network. So if something increases, you will be able to see, and you will be able to act in consequence. You will be able to escalate, maybe add an interface if your traffic goes up. But I can assure you that it's almost impossible that the network traffic is going to be an issue when you enable DNSSEC in your resolver. Okay. One other thing to consider is that when you enable DNSSEC, when you are doing DNSSEC verifications, the authoritative server is going to be sending you more information, right? and it's going to be sending you that information even if you don't have DNSSEC validation. So if you operate an authoritative server, when you send the information to a resolver, you're going to send more information because now you are sending keys, you are sending signatures, etc., plus the data. So DNS packets are going to be longer, are going to be bigger. It may happen that that information does not fit into a UDP packet, and your for some responses, your server may start using TCP. Just bear in mind that DNS needs UDP and TCP, because if the information that is being exchanged does not fit into a UDP packet, it will set up a connection and it will use TCP. So make sure that your server does support, and your firewalls and all your security measures allow for UDP and TCP exchange for DNS traffic, right? Again, this is not new. This is not something that you are going to be doing because you have now enabled DNSSEC. This is something that you've been doing always. You've been always doing if you administer a DNS server. Make sure that your server can use either UDP or TCP. Okay. Other thing that is very important if you operate a DNS server is, especially when you enable DNSSEC, and this is especially when you enable DNSSEC, you will have to make sure that the time of your server is the correct one. So you will probably want to configure, if not already done, you will probably want to configure NTP, Network Time Protocol. So your server is always with the correct, the clock, the time reference of your server, it's always synchronized with the world time. Because why? Because each signature, when you receive signatures, when you receive responses from an authoritative server, those responses have a time tag. So each response is associated with a time, and that response will be valid only for a certain period of time. So if your server is not synchronized, let's say your server is off for 1 hour, and the information is only valid for half an hour or whatever, it can happen that you receive the response, but when you compare the time of your server with the time valid for the response, your response is no longer valid, and your server will discard the information and won't be able to verify. So it will give an error because it will think that information is fake. So your server, if you enable DNSSEC, your time has to be synchronized. Okay. So use NTP. This is something that it's also recommendable even if you don't have DNSSEC, but just bear in mind that DNSSEC uses time synchronization as an essential part because each response has a valid period of time. Okay. Even when you generate your private key and your public key, you have to tell the amount of time that key will be valid. If you are rotating your key every 6 months, you are generate a key probably that it will last for 8 months, right? Because you will probably want a buffer there. You won't set the the time frame for the exact period of time you rotate the key. So if you rotate the key every 6 months, do not create your key with 6 months validity. If you rotate your key every 6 months, just create a key for 8 or 9 months. Okay, so you have time to perform the rotation. Okay, but anyway, if you receive a key that is out of that time frame, it won't verify. Okay, it will give an error. Okay, that's all. That's those are some good practices or recommendations or stuff that you have to bear in mind when you are dealing with DNSSEC. I hope this helps you to understand a little more, at least, about how DNSSEC works. I hope now you have a clear and a good idea of what is DNSSEC, what that provides, and how it works. Again, this is not essential to be able to do the following activities like the hands-on lab. This is not essential to operate a DNSSEC enabled server, but it's always good to know what happens behind the curtains when you are operating stuff, because it helps you if you have any issues, or if you have to debug something that is going on. It's always good to know what is happening, to be able to say, let's see if this is the problem. Let's see if my key is outdated. Let's see if I have the correct DS record in my folder, or something has gone wrong because this is not validating. Let's see if, so if you know what happens and how things function, it's better it's going to be easier for you to operate and to administer your servers, right? I don't know if there's any question up to this point. Again, feel free to throw any question. You'll also have our emails, so you can contact us, Daniel or me, at any time. You can ask us any question about all of these presentations and all of these protocols. Okay, Daniel, I don't know if there's any question.
Well, sure. We have time for your questions. Your comments are always welcome. If you allow me, I would like to share with you this quick evaluation for us. It is very important. Thank you in advance for providing us some feedback. And if you have any comment, any question, please do so. You can raise your hand or open your microphone. We have some time to interact.
Meanwhile, you feel the evaluation. Let me just tell you that the presentation is going to be, if you do not already have it, it's going to be. I already sent the presentation, so you will get the PDF with the presentation. The recordings of this will be sent to you also, so you can go and see it again. For example, if you're having issues at night with sleeping, you can just look it a couple of times and read it a couple of times, and I'm sure you're gonna fall asleep. And being serious, any question you may have in the future, just feel free and send it to us. We will try to answer you as fast as possible, or if the answer is a little more complex, we may arrange for a call or whatever, in order to help you in your daily activities with this DNS and DNSSEC. So anytime, feel free to contact us at any time. Okay. And yeah, as I was saying, I hope this helped at least a little bit for you to understand how DNSSEC works, and how important is to be able to enable DNSSEC, whether you are operating a resolver or an authoritative server. It's something that it has been around since 2010. For over, that is over 12 years now. And yeah, it's not a huge widely adoption yet, but yeah, it's something that I think in the future should be adopted and should be deployed by every operator, whether you are an authoritative or a recursive server operator.
Many questions are popping up, Nico.
Okay. You want to read it?
Yeah. Rohan, okay. Thank you, Rohan. You did mention the DNSSEC validation in the coming lab for the resolver. Will you be demonstrating the DNSSEC setup on a zone for the authoritative server?
Okay. What we will do in the next 3 sessions is that I'm not going to demonstrate. You are going to configure your own resolver. Yeah. What about, you're asking about the authoritative, the other side of the equation, right? If you run an authoritative server, how to configure a zone and how to sign a zone. we are not doing that in the next meeting. Actually, we have not planned for that specific capacity building in this yearly capacity building plan, but for sure we have that capacity building in our curricula, and we can provide. We now that you have the need, or you want us to present on that, we can arrange to have a practice and a hands-on lab where you can configure your own authoritative server, sign your zone, and even rotate your zone. We have also tracks about capacity building instances for you about DNS operation and DNSSEC operations, which is a full and different capacity building program, because there are many things that you have to take into consideration when you run an authoritative server. But yes, we can do that. We can do that for sure. Let's find a time window to be able to do that. I always prefer, if you, I don't want to demonstrate how to do that. I want you to do that. So that's a different stuff. When you have someone demonstrating you things, and then you go home or you go to your job and you say, "Oh, this is fantastic, but I don't know where to start. I don't know what to do." On the other hand, if you try the stuff, if you face the issues, if you configure stuff, that is far better, and that is for sure helpful in your day-to-day job if you run a server. So let's try to arrange for a hands-on lab where you configure your own authoritative server and you sign your own song, and we do the rotation, and we will do that. Okay, Daniel. So let's try to arrange to include that in a presentation in the future. Let's do that.
Okay. So from Hyukia, thank you, Hyukia. Nico, you skip a section, one slide or two during the presentation, just before the explanation of the DS records.
Yeah.
Yeah.
The short answer is no, but I'm going to explain why. What I skip is one or two slides that we actually skip it, while we actually talked a little bit about that. So we covered it, but very fast. What I skipped is the way that specifically which resource records are signed with which key and how that is transferred to the father. But you can go through those slides yourself, and you will understand perfectly, and I think you will be able to understand correctly how that works. If you have any question about that, just send me an email, or send Daniel an email, and I will explain it with more detail. But in the hands-on, we don't need that for the hands-on. Actually, again, you don't need all the specifics of how this thing internally works. So everything we explained it's not fully necessary in order to perform the hands-on lab. You're going to be able to, you'll see that you're going to be able to configure and make things work. And also, if you have any issue, you will be able to debug and to solve issues without remembering exactly how this internally works. But again, of course, it's very useful to know how things work. Again, go through those slides. If you have any questions, just drop me an email. I'm going to write the email again in the chat, my email, so you have it. Okay.
And from Richard, Nico, if a third party hosts your DNS, is there a way to get your zone file?
No. Because why? Because normally no. Normally the short answer is no, because zone files are normally something that is kept by the one that runs the server. It's not that you cannot know the content of the zone file, because it's public. I mean, everybody's authoritative servers by definition have to be public. But one thing is for you to be able to query specific content of the zone file, and another one completely different is to get the whole zone file. If someone runs the DNS server for you, means that you have one or two or three or a few domains that you put into a certain zone file. But the zone file has your domains and a lot of someone else's domains. So you're not going to get the whole zone file. What you, of course, you can do, and you don't need to talk to anyone. We are going to see that during our hands-on. For sure, you can get for your domains or for any domain, you can get all this information. You can get the public key, you can know the digital signature, etc., the DS record, etc. You can get all of that information by using the dig command, as we are going to see in the next sessions. Okay, but you're never going to get the private key, and you're never going to get the whole zone file. Okay.
Mm-hmm. I think this question is connected to the next one from Rohan. Said like bind application nowadays automatically configures DNSSEC validation. Is there something else you want to bring to our attention on the resolver side? So let me start, Nico, if I may.
Yes, of course.
It's true, Rohan. It's very interesting that both bind and unbound are now coming by default with the DNSSEC validation configured, which is very good. I think it's a great motivation for all of us to have DNSSEC validating in the resolver side. What we're gonna do in the lab as well is a lot of exercises for troubleshooting. So we will use, as Nico mentioned, the dig command. So you can do some very specific queries to your zone files, and we can make sure that DNSSEC is validating, whether it's not, how to monitor our servers for during the day-to-day operations. So we will demonstrate how to enable DNSSEC, how to disable, and how to do a lot of checkings in the system. So we believe that for the ISP, it's very important to be ready when some customer calls you. Oh, I have a problem going to this website or not. So how can you identify if this is a sort of attack or if this is just a misconfiguration in the authoritative side, and so on? So that's what we are going to spend time during the lab. Thank you. Don't know, Nico, if it's... Okay.
Yeah, I mean, you name it. I mean, it's if you install, whether you install bind or whether you install unbound or any other DNS resolver server application, it will be likely to have by default DNSSEC enabled. What happens is that some of DNSSEC DNS server resolver administrators have been running a DNS server for years. So you'll probably started with early versions of these servers that do not have DNSSEC enabled by default. So in those cases, you'll probably, whether even if you updated and you are running now the last version, it may happen that you don't have this by default enabled. Actually, some people, when they update, and they, even if the default behavior is to enable DNSSEC, they will, insert an option to disable DNSSEC because they don't have DNSSEC. They don't want this to go enable from one day to the other without being noticed. So some administrator disable DNSSEC on purpose before updating. The ideal thing to do is to enable DNSSEC, but in a controlled and planned manner. So if you are starting with a resolver, you will have DNSSEC enabled by default. And my advice is to not disable. If you are starting, just start with all the features. That's the best way. And if you have an older resolver and you are not yet validating DNSSEC, just plan for enable DNSSEC validation and enable validation and give it a try. I can assure you that it's not going to give you big issues. Just the normal stuff you have to monitor, and you have to, keep an eye on new things that will be happening at the resolver level. That is validation. And we will see that in our next sessions, and we will give you some clues and some tips for you to debug and to operate a resolver that has DNSSEC enabled. Okay. NSEC, the NSEC stuff, right?
The NSEC.
Yes. I forgot about it. I promised to talk about it and I forgot it. What is NSEC? So we mentioned that DNSSEC has these two main features, right? It provides origin authentication, and it provides with a means for data integrity. So you are sure that no one tampered with information. But what happens if you are trying to find, for example, say the IP address for a domain name that really does not exist? So you're asking the DNS for something that is not in the DNS. Normally, if you don't have DNSSEC enabled, DNSSEC will answer with a NX domain message. The response will say it will have the NX domain message on, that is non-existing domain. So that is the way an authoritative server is telling you that the domain you are trying to find information for it, the information you are trying to find, does not exist. That could happen. If I ask for blah 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 .com, probably blah 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 .com does not exist. So I'm going to ask the DNS, I'm going to get, okay, that domain does not exist. Okay. If you have DNSSEC enabled, DNSSEC also provides a means for you to be able to sign to generate a digital signature for the negative responses. So when the authoritative server tells you that that domain does not exist, if the authoritative server has DNSSEC enabled, the authoritative server is going to actually sign that negative response. So it's going to tell you that that not exists, and it's going to sign it. It's going to generate a digital signature for that negative response. So when you get that response, you are going to be able to verify that that negative response really comes from the authoritative server you are getting information, and it's the truth. It's not someone that is making you think that that does not exist in order to prevent you from accessing a certain domain. So what is NSEC? NSEC is the signing of the negative responses. NSEC is the protocol that specify how to sign, how to generate a digital signature for negative responses. NSEC has basically two flavors, NSEC and NSEC 3. Don't ask me what happens with NSEC 2. It never existed. It's NSEC and NSEC 3. As many things in life, for example, IPv4 and IPv6, and what happens to IPv5? IPv5 never existed. Okay, NSEC 2 never existed. This is NSEC and NSEC 3. NSEC 3 is kind of upgrade to the protocol that prevents some specific flaws that the original NSEC specification had. Basically, something that is called to be able to walk a zone file. We can talk about that in the future. There's no need for us to get into details about that. Just that NSEC 3 is the protocol that specifies how to sign negative responses coming from the authoritative server. So it comes with DNSSEC, and every authoritative server will either use NSEC or NSEC 3 to sign its negative responses, right?
I think the question from Nicholson is very interesting. It said like some clients with NSEC 3 say they are protected. So I think your answer, Nicholson, would be like, so if you are enjoying NSEC 3, I think you already have DNSSEC, yes. Right? So yes. Because NSEC is a feature of DNSSEC. So yeah, I think you can tell them that they are good to go.
Yeah, I mean, it's not something, it's not one or the other. It's you can have NSEC or NSEC 3 enabled. You can have that disabled, if it's true that comes with DNSSEC, but it's also true that you can disable NSEC at all. You can only have DNSSEC. It's very strange, and I've never seen servers only having NSEC and no DNSSEC enabled. It's kind of weird because it's, if you are signing negative responses, why not signing all, right? So you have the same amount of work, and probably what you will have to answer, my answer to the people asking that is, are you sure you understand you're not having your record signed? Are you sure you're not using DNSSEC? And you can verify that. You're going to see in the next presentations how to verify that a server has DNSSEC enabled, and how to verify that if it has NSEC or NSEC3 also enabled, and you will be able to do the verifications and send a response with examples to the client that is claiming they don't need DNSSEC because they have NSEC3. It's very, 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 very rare that you have one and not the other one. Yeah.
One more from Rohan, interesting one, that most bind security update seems to relate to DNSSEC. Do you get the sense that after enabling DNSSEC, your DNS platform becomes more vulnerable, especially if frequent application updates are not completed? So I think there are many ways to see this question. So first, DNSSEC is a protocol for making sure the service is performing with more layers of security, right? So addressing some vulnerabilities of the DNS itself. However, sometimes the software applications are not perfect. No one are. So, and I'm sure that bind, the software engineers, Unbound as well, they are very thorough on trying to fix all vulnerabilities. So it's possible that there are more fixes are done to the DNSSEC part, but it doesn't mean that DNSSEC is not a secure protocol to be utilized, especially because bind is very complex, right, Nico? Bind can do authoritative part, can do recursive part, can do even both, although this is not recommended, right? So it's possible. So I think one of the recommendations we always do is like when you have some operation, you always have two servers, both authoritative. You have primary, you have secondary, both in the recursive part, right? So if you want to make sure that your software is working well, you can use two different softwares, right? So one idea could be like if you have a bind as your primary server, maybe you could have some Unbound as secondary server. So you, while you are fixing some updates, which you have to do all your life, right? You can rely on the other one, right?
Yeah. And also, Daniel, just my short answer will be, if you have DNSSEC enabled, you're always more secure than only with DNS. I mean, it's always better. DNSSEC it's a protocol that has been around for over 10 years now, and it does not once you have it in place, it does not add more issues or more security breaches. In fact, it solves a lot of them. So it's always better, and it's always a more secure infrastructure if you have your DNS infrastructure with DNSSEC enabled compared to not having DNSSEC enabled. Okay. All right.
Thank you for your answers.
Thanks again, Daniel.
I will close the pool.
Okay.
Thank you very much for your answers in the evaluation. And we will be together again on August 2nd, right? For the laboratories. So we will have 3 sessions in a sequence for setting up the lab, configuring bind, and configuring Unbound. 3 sessions. Thank you so much for your active participation, your questions. It was very interesting for us. We hope it was interesting for you.
Thanks
And
very much, and thanks for being with us today, and see you next time. And I hope you enjoy the presentation. And again, any question you may have in the future, feel free to send to us. Have a nice day. Bye-bye.